All right, so let's talk about some other units of concentration that you might encounter in different fields. In chemistry, we typically use the concentration unit molarity, which again we talked about in the previous video. Is molarity is moles of solute over liters of our solution. And so the higher number your molarity is, the more concentrated the solution is. And so the lower the number, the less concentrated. So you kind of see this picture here. How can we convey more concentrated solutions versus less concentrated solutions or more dilute solutions? And so that's all based upon how much solute is dissolved in your solution. So that's the basis of these other concentration units. How can you convey how much solute is dissolved in the solution? So there's a couple ways that other fields of study, different like engineering, agricultural businesses, the medical field, oftentimes will use different concentrations. And so those other concentrations that we'll talk about and those units are percent by mass, percent by volume, and mass by volume. So let's just go through those different units. But again, all of these different units just convey, concentrated samples and dilute samples. How much solute is dissolved in your solution. Okay. So the first one is percent by mass. So this one's often used in engineering, agricultural applications. So the unit of percent by mass is you take the mass of the solute that's dissolved and divide that by the mass of the total solution. And you multiply it by 100 to get it into a percent. All right, and so, for example, if we have a 6% percent mass concentration of a substance, what that means is that there are 6 grams of solute dissolved in 100 grams of that solution. So if we kind of break that down, because remember our solution is always composed of your solute and your solvent. So if it's water or something, that means if 6 grams of your solute is there, that means in 100 grams of solution, that means that there must be 94 grams of solvent present because, again, both solute and solvent make up your total solution. Right? And so, yeah, percent by mass, you just take the mass of solute over solution. So remember our molarity unit was moles over liters. So this case, it's just a different way, different units to convey how much solute is dissolved in your total solution. Do I give an example here? Yeah. So milk is oftentimes the fat content of milk is oftentimes expressed in a mass percent. So like 1% milk that you might get at the grocery store is 1% by mass of fat of that particular kind of milk. So in 1% milk, it means that 1 gram of fat is present in 100 grams of your milk sample. So that means one gram of fat, that is your solute. I can spell solute. And then there's 99 grams of other things like water, proteins, casein, other things. But 1 gram of that 100-gram sample is milk. And then 1 gram of fat is your solute. So then, for example, if you had 2% by mass milk, if you buy 2% milk, that means you have 2 grams of fat for every 8. I can do that. 2 grams of fat for every 100 grams of milk. Simple as that. So that's percent by mass that you might see, like on a milk carton when trying to express fat content. So another concentration unit that you might see is percent by volume. So we are expressing the amount of solute and solution in volume. It's simple as that. So typically this type of concentration unit is used when both the solute and solvent are liquids or gases. And I'll show you an example. Because liquids are easier to measure in volume instead of mass. So that's why we'll often use volume, percent by volume. So percent by volume, similar to mass, it's just now you use volume instead. So it's the amount of solute in volume that's dissolved in a certain volume of your total solution, and then times 100 to make it a percent. So an example here, if we had a 17.0, oftentimes we'll put V over V to mean volume, percent by volume. That means if we have 17%, that means that there's 17.0 milliliters of solute which typically can be measured as a liquid, dissolved in a total of 100 milliliters of solution. So in total, if the solution is 100 milliliters, that means 17 milliliters is your solute, and then 83 milliliters is your solvent, because your solution is 100 milliliters. Right? So percent by volume, you just think about solute in terms of volume. So an example of percent by volume is something like rubbing alcohol. If you grab a bottle of rubbing alcohol, typically on the bottle, it will say it's 70% volume of alcohol. So that 70% is actually a volume percent. So 70% alcohol means that in rubbing alcohol, so if it's 70%, that means 70 milliliters of alcohol is your solute, or is the thing dissolved, and then 100 milliliters of your total solution. So that means that there's 30 milliliters of something else. So in this case, it's water. So in this example, alcohol is not our solute here because it's actually present in the larger quantity. So, where I said solute over solution, in this case, I just mean it's the thing dissolved in the total solution. So in this example, since 30 milliliters is water, 70 milliliters is alcohol, water is actually our solute, and then alcohol would be our solvent. So that's just kind of a detail that you might have missed. But in general, these volume percentages still mean the same thing. If it's 70% volume alcohol, then that means of 70 milliliters will be alcohol in a 100 milliliter total solution of the substance. All right. So that's our second other unit, concentration unit we can talk about. Then lastly, we have one last concentration unit that is often used in the medical field. So I know a lot of you are in biology, dentistry, those majors. So you will oftentimes see percent weight by volume in different medical applications and things of that nature. So this is used in the medical field where you dissolve a solid solute in water. So with percent weight over volume, it's just as straightforward as that. You take the weight of your solute in grams and you divide it by your volume of your total solution. So you see a reoccurring theme here that the denominator is always like volume or mass of your total solution. So same thing here with weight volume percentage. It's grams of your solute, so weight, over volume of the solution, and times 100 to make it a percentage. So I have a question here. If you in the medical field, you might have seen things like IV bags. IV bags are a salt solution. And so, what is the weight volume percentage of a IV bag if 750 milliliters of solution contains 6.8 grams of sodium chloride? So here, sodium chloride is our solute. So there's our gram amount that goes in the numerator. And then our volume, which is 750 milliliters of solution, that is our denominator. So to calculate weight volume percent, we do 6.8 grams of sodium chloride over 750 milliliters of solution times 100 to get, do I have this somewhere? No, I didn't write it out. Why didn't I do that? So 6.8 divided by 750, that's how much grams of sodium chloride is dissolved in one IV bag times 100 to give us a percent. So this is 0.906%. We want 2 sig figs here. So 0.91% sodium chloride weight volume. All right, and sodium chloride, yeah. So if you've used IV bags, if you volunteer at the hospital or work at the hospital, you might have seen on the IV bags it typically says 0.9% weight volume sodium chloride. So that is how much 6.8 grams is how much sodium chloride is actually dissolved in those IV bags, but instead of expressing it in something like molarity, they will express it as a weight volume percent, just because it's easier to visualize, how much sodium chloride is actually dissolved in that IV bag. It's easier to prepare on the medical field side of things. Just weigh it out, dissolve it to 100 milliliters or whatever. So that is the weight volume percentage of an IV bag. Okay, so let's kind of expand on percent weight volumes. There are also other ways you can express weight volume concentration. So for very dilute solutions, oftentimes concentration will be reported in units of parts per thousand, parts per million, or parts per billion. So you might have seen things like that, like, lead concentration in parts per billion in like drinking water or something like that. So those terms, parts per thousand, parts per million, parts per billion, that comes from or is related to your percent weight volume. So this calculation. So you want to think about, grams of your solute over milliliters of solution. This will help you get to parts per thousand, parts per million, parts per billion. Because the equation to calculate these different concentrations is essentially you take the weight volume portion of our weight volume percentage, but then apply different multipliers to it to get to parts per thousand. So to get to parts per thousand, you multiply this number, your weight volume, by 1,000. So 10 to the 3, that's 1,000. To get to parts per million, you take that same weight over volume ratio, but this time you multiply by a million. And to get to parts per billion, again, it's the same thing, but you multiply by a billion to get to parts per billion. These different units are applied to very dilute solutions because these different multipliers will change where that decimal place is, so you can read the number more legibly. So the last slide here, I'll show you an example of how we can use parts per thousand, million, and billion. So in this problem, again, we're thinking of weight over volume ratio, that percentage, weight over volume, or that kind of concentration unit. So many cities add sodium fluoride to drinking water to prevent tooth decay. So if 25 liters of city water contains 0.018 grams of sodium fluoride, what is the concentration of sodium fluoride in parts per thousand, million, and billion? So my strategy here will be to calculate the weight over volume ratio. Because if we look back at, this slide, parts per thousand, million, and billion, we need this ratio, and then we will apply the different multipliers to get thousand, million, and billion. I will point out that we're not taking the percentage, so we're only taking this ratio, the gram over volume in milliliters of the solution. So don't apply the 100 because that's what makes it a percentage. So we're only taking this ratio. So let's identify what is the solute, the grams of solute, and what is the volume of solution. So if we take a look at the information given, we're given a volume and we're given a mass of solute, which is great. So here is our mass of solute, sodium fluoride. So that's our numerator. But now we need volume, but it needs to be in milliliters. So we can't keep it in liters here. So, 200 or 25 liters, we want to convert that to milliliters. So 1 liter is 1,000 milliliters. So this is equal to what? 25 times 10 to the 3 milliliters. So that's what we'll put in our denominator as volume, total volume of solution. So our weight over volume will equal 0.018 grams over volume in milliliters. So 25 times 10 to the 3 milliliters equals something, equals 7.2 times 10 to the negative 7 grams per milliliter, I guess. I guess that's the unit. So if we wanted to convert that to, a percentage, like if we wanted to convey the weight percent, it would be a small number. It'd be hard to kind of see. It would be 7.2 times 10 to the negative 5%. So that's like a really small percentage. So this is why conveying numbers in parts per thousand, parts per million, parts per billion is a little bit easier on the eyes to see those numbers. So now that we have weight over volume, that ratio, to calculate parts per thousand, we just multiply this number that we just calculated by 1,000. So parts per thousand is that number times 10 to the 3. So it is equal to 0.00072 parts per thousand. So that's the unit we use there. All right, and so that number is still pretty small too. So 1, 2, 3, 4. It's 7.2 times 10 to the negative 4. So that's not that great on the eyes. So let's see what this number looks like in parts per million. So again, take that same number, the same weight over volume ratio, but this time multiply by a million times 10 to the 6th. So that is equal to 0.72 parts per million of sodium fluoride. I guess I should add that. All right, so that number is a little bit easier to see, 0.72 parts per million, yeah. Let's just do parts per billion. So ppb is the same ratio, but times 10 to the 9, yep, a billion. So that is equal to 720 parts per billion of sodium fluoride. So typically, when reading literature about, fluoride concentration in drinking water, you'll oftentimes see it in expressed as parts per million or parts per billion, because these numbers are easier to read in general because they're larger numbers. They're not like tiny numbers like parts per thousand or our percentage weight volume percentage. All right, so you'll see units like this oftentimes in lots of different places. So understand that parts per thousand, parts per million, parts per billion comes from weight volume percentages. All right, okay, so that concludes composition of solutions. So this is where midterm 1 will stop. I will be posting numerous practice problems for you and a practice midterm for you to practice the skills that we've learned in the past 3 chapters. And then the next section will be chapter 4, where we will be going over chemical reactions.